Okay, so let us go to the next important point of this lecture. And the title of this new chapter is Point of Accumulation, or Accumulation Point, more briefly. Allora, points of accumulation. So, the idea of point of accumulation is quite simple, and the name is sort of self-explanatory, because here you have the real line, and here you have x bar, and the set E is made somewhat, somehow, somewhere, and so on. So, I want to understand what does mean to say that the set E accumulates at a point x bar. It basically means that a lot of points of E concentrate around x bar, but let's be more specific. The idea is that you can get closer and closer to x bar, remaining in the set E. Exactly the notion that we need in order to define limits for x going to x bar. So the idea is that what does it mean to get arbitrarily close to x bar? It means that whatever distance you take from x bar, so whatever neighborhood of x bar you consider, there are points of E falling in this neighborhood. Okay? So here the naive idea. There is a problem here. Okay. Naive idea is the following, in a very bad language, very bad, not English, also English, but mathematical language, very bad. So there are points of E that are arbitrarily close I want to stress that the idea can be effectively expressed by saying that, but mathematically speaking, it is a poor way of expressing it, because it must be reversed. So, however close you go to x bar, there are points of E that are closer to x bar than you. This is the correct idea. So the synthesis says there are points of E arbitrarily close to x bar. This is not correct. I hope you believe you are able to grasp this difference. However, I give you the definition, and when you are asked by someone what is an accumulation point, give it or her not the naive idea, but rather the rigorous definition. So, rigorous definition is the following: let E be a subset of R. So, a point x bar in R is said to be a point of accumulation of E, of the set E. When you say point of accumulation, you always mean point of accumulation of a set, of a certain set. Okay? If here the definition, for every neighborhood of x bar, which means for every element of the set ux bar, a set of all neighborhoods of x bar, there exists a point x which is in E and is not x bar, such that x belongs to this neighborhood. Okay? Let us read together this definition. I'm telling that for whatever neighborhood of x bar, which means however close I go to x bar, there is, sorry, this is a mistake, not an x bar, there is an x. There is an x in E, which is not x bar, such that this x is in that neighborhood. However close I go to x bar, there is a point in E which is not an x bar, and that is closer than me to x bar. This is the idea. Okay? Okay, we can also restrict the definition to spherical neighborhood. It doesn't change anything. It is heavier somewhat. This is more abstract. This is more elegant. But if you don't like neighborhoods and you like epsilon, deltas, and numbers and so on, you can use the other definition, or equivalently, for every delta larger than 0, there exists x in E such that the distance of x and x bar is less than delta. But here I want to specify that x is not delta, so I write 0 strictly less than that. Okay? Okay, this is written just to state that in this definition we require that x is not x bar. Okay. Of course, the difference between these two definitions is that the first is most general. It seems to be most general, more general, because here we use neighborhood, not only spherical neighborhood. In the second one, there is a delta appearing, so we are using only spherical neighborhoods. But in reality, you can think of it, we can pass from one definition to the other. So they are completely equivalent. Okay? So, another remark. I repeat always the same thing in different languages because I hope that at least in one way you will get it. So the notion, you will get it. Today my English is worse than usual, but so there is no possible solution to this problem. So the notion of point of accumulation translates mathematically, rigorously, the idea of getting arbitrarily close to x bar, remaining in E. But not in x bar. This is the idea. Okay, let me discuss an example, and it is very similar to the previous one, but it is not exactly the previous one, because instead of the square root, we use the logarithm. We consider the function f of x is equal to log of x squared times x squared minus 4. As a domain, we choose the largest subset of E for which the analytical expression I wrote is meaningful. So, with logarithm, we ask that this argument is strictly larger than 0. This is the difference between logarithm and square root. When you have the square root here, like the previous video, what you ask is that here inside the argument of the square root is larger or equal to 0. But if you are dealing with a logarithm, the only thing you need is that larger than 0. Equal to 0 is not good because there is no logarithm of 0. Logarithm is not defined at 0. Okay? So here it has changed with respect to before, so this time E, the maximal domain we can use in order to define this function, is the union of two open intervals minus infinity minus 2, union 2 plus infinity, and there is no 0. There is no 0. Okay? We introduce another symbol, which is just a symbol, and this is dE, and the so-called derived set of E. This has nothing to do with derivative, just a name. And this is simply the set of the points of accumulation of E. I don't want to use the definition and so on, but the idea is that you are here, this is E, and you want to know to which points you can get arbitrarily close by remaining in E. Of course, these are intervals, and in all points of the domain you can get arbitrarily close because it is an interval, but then, moreover, you can get arbitrarily close to minus 2 and to 2. It's minus 2 and to 2. So this d turned out to be minus infinity minus 2, closed, not opened, union 2 plus infinity. And so if you are concerned with the computation of limits of these functions for x going somewhere, so that somewhere, that x bar, must belong to this set. Otherwise, it is meaningless to ask for the limit. I hope this is clear. Again, if it is not clear, then listen again. Try to figure out by yourself what happens, and I can help you, as usual, with a picture. So this is the picture. Here you have minus 2. And this is E, the red set is E. Then here you have plus 2. Okay, this guy here is E. And what I told here, introducing this derived set, is the following, is that you can get closer and closer by remaining in E to every point of E, but you also can get closer and closer, arbitrarily close to the point minus 2. And to the point plus 2 by remaining in E. Okay, is it clear? Another example. And the example I chose here is the set E, which is the set of the inverses of natural numbers. So we have, of course, non-vanishing natural numbers, 1 over n different from 0, n natural. And so let me represent this set here. And remember that here you have 1, 1/2, 1/3, 1/4, 1/5, and so on and so on and so on. And then you can get closer and closer to 0. You can get here closer and closer to 0 without being 0, but no other points can be approached arbitrarily close in all the real line. Try to think of that. I don't ask you the rigorous proof because it will be extremely boring. but the conclusion is that the set of the accumulation point of this set E is the only point 0. Notice that here I'm not studying a sequence, okay? I'm just giving you a set, and this is the set, and asking you who are the accumulation points of the set. So this is just the question. You don't have to think of functions nor of sequences. Okay. So from this, I hope that it will be quite easy for you to understand the following point. So a finite subset of R has no accumulation points. This is quite easy to be represented, of course, because you have here a finite number of points that fall into your set. And when you finish, of course, none of these points can be approached arbitrarily close by remaining into the set, nor other points in the real line. Remember, you have to approach them without using them. You have to approach them by other points in the set A. And more intriguing is the other example, which is the following: an infinite and bounded subset of R and this is the result, always has an accumulation point. This can result quite counterintuitive or difficult, or counterintuitive not. But this is the one version of the Bolzano-Weierstrass theorem. I already gave you a Bolzano-Weierstrass theorem for sequences. This is an almost equivalent theorem to that, not completely equivalent. So we are in the version of points of accumulation. Okay, so the end of this lecture is here. I don't want to prove this theorem, but take it as an information and use it in some points during the course. But if you want, the proof is for you as a homework. And I prefer to stop here this video, even though it is shorter than usual, because from the next video I start with the rigorous definition of a limit of a function. Okay?